Thank you very much for the kind introduction. Today I'm here to talk about how to use site isolation to denial of service your browser, your operating system, or even to implement a DNS cache poisoning attack in the web attacker model. Before we delve deeper into the attacks though, I want to give a brief overview over how site isolation changed multiprocessing in browsers. Prior to site isolation, in the process per tab model, a new process was created for each new window or tab. And if multiple sites were rendered in the same window or tab, those sites would share the same process. In contrast, site isolation creates a new process shared between all instances of the same site regardless of how many windows or tabs the site is rendered in. Additionally, with site isolation, process creation became fully automatic. Prior to site isolation in the old process per tab model, process creation required explicit user interaction such as opening a new window or tab or confirming pop-up dialogues such as those highlighted here in the screenshot. So site isolation provides attackers with the power of process creation. Let's take a look at how an attacker can use those powers to create a fork bomb in the web attacker model. Imagine an attacker who owns an IPv6 address block and hosts a website attacker.com. The website attacker.com contains an iframe that points to one of the attacker's IP addresses, and visiting the site will simply create two processes, one for attacker.com and one for the IP address shown. And the iframe now references a different attacker website that embeds two additional iframes that reference two additional IP addresses, creating two additional processes. And if the attacker now continues to recursively embed iframes into that site, we have a fork bomb in the web attacker model. If you have ever visited a poorly programmed or malicious website in your browser, you might have encountered Chromium's or Snap dialog or one of the pop-up dialogues shown here that inform you that the page is being unresponsive or slowing down your computer. And you may expect those mechanisms to protect you from the site isolation fork bomb. However, this is not the case. In case of the site isolation fork bomb, what usually happens is that either your browser will crash or freeze, or even worse, your operating system will freeze or even black screen. So why does the browser fail to detect and prevent the site isolation fork bomb? There are two problems at play here. First, we have an attribution problem. Actually, the browser has no information about who operates the site. So if we look at all those IP addresses here, the browser cannot know that all the IP addresses actually belong to the attacker. It has to assume that all are unrelated sites and thus isolate each and every one of them. The second problem is the monitoring problem. While existing resource monitoring mechanisms can detect resource consumption within the browser sandbox, the attacker website merely contains two iframes, so the majority of the resources consumed are not consumed within the sandbox, but rather by the browser itself, trying to isolate a large number of seemingly unrelated sites. But there are other problems. Site isolation provides access to secondary resources. Let's take a look at the Chromium source code. As you can see here, Chromium defines a limit of 3,000 sockets. And in case this would be a global limit, this could raise a potential problem. If an attacker website would simply allocate 3,000 sockets, no sockets would be left for other sites to use, resulting in denial of service. However, Chromium does things differently and limits sockets per process. And in the old process per tab model, that was advantageous because if an attacker exhausts the entire resource pool in a single tab, other tabs would still remain functional and websites would still be able to operate. With site isolation, however, things changed, and one window or tab can now denial of service the entire operating system simply because an attacker has the power to create arbitrarily many processes and thus exhaust the entire socket pool. So now let me show you how you can use those capabilities to perform a DNS cache poisoning attack against the Windows 10 client in a web attacker model with a median attack time of 3.5 minutes. The attack will exhaust the UDP ephemeral port pool of a victim operating system using the site isolation resource limit bypass and misappropriating WebRTC to create many island network sockets. This forces the victim operating system to use a fixed DNS query port instead of a random one. We call this attack DNS poisoning by exhaustive misappropriation of network sockets, and because that doesn't really roll over the tongue, we nicknamed the attack Demons. Due to time constraints, I cannot go into too much details about demons, but I will try to give a brief overview over how the attack works. So the attack starts with the victim visiting the attacker's web server. And as you can see here, the UDP pool is almost entirely available to the victim operating system. Now, the attacker website is loaded by the victim's browser, and the malicious JavaScript is being executed inside the browser sandbox. And the browser will start to allocate sockets, eventually running into that 3,000 socket limit defined by Chromium. And at that point, a significant portion of the ports has been used, but as you can see, there are still plenty of ports free for the operating system to play with. However, what the attacker can do now is they can embed additional sites within their malicious site, each containing a copy of the malicious JavaScript. And because every one of them runs in an extra process, each of them gets an extra limit of 3,000 sockets, and they exhaust the entire ephemeral port pool of the victim operating system. So at that point, we simply have a denial of service attack because the victim cannot create any UDP sockets anymore, and thus DNS resolution wouldn't work. However, we don't want to implement a DOS attack. We want to create a DNS cache poisoning attack. So what we do now is we release one socket back to the operating system and leak it via WebSocket to the attacker's poisoner. So now the attacker knows which DNS query port will be used by the victim and can start to send spoofed DNS responses for a domain of their choice. Those responses are in transit, and while that happens, the malicious JavaScript that runs in the victim's browser triggers an XML HTTP request that triggers a DNS query for the same domain. And at that point, the victim operating system will start to accept responses. And once a spoofed response arrives with a transaction ID matching the query, the victim will simply write the malicious entry into their cache. And from now on, every time the victim contacts bank.com, it will instead be redirected to the attacker's malicious server. The daemons attack was mitigated via a global port limit. This has some drawbacks. So for one, it may not suffice if multiple browsers are in use at the same time. And second, as we saw before, such global limits can enable DOS against the browser. The site isolation fork bomb, however, is currently not mitigated. We have proposed a countermeasure though, and we even implemented a proof of concept patch for Chromium. And now I will give a brief overview over how a production-ready implementation of our proof of concept could work like. So our idea here is to limit the number of processes or sites that can be created per tab. We define a limit L, it's a predefined fixed value. In this case, I will use the value 4 for the example. And when a tab is opened, this tab will get a tab local limit L1 that is initialized with that value of L equals to 4. Now, if a victim again visits the attacker's website, the attacker website is loaded, and of course site isolation is going to isolate the attacker's site, creates a new process, and because one process is created, this limit is reduced by 1 to the value of 3. So now if the attacker executes the fork bomb website we've seen before, an iframe is loaded, and this iframe points to one of the attacker's IP addresses, creating a new process and reducing the limit to the value of 2. Now we have 2 running processes, and the attacker will proceed to embed more iframes, each referencing a new IPv6 address and creating 2 more processes. At that point, 4 processes are running, which is exactly the limit we defined, and we arrived at 0. So now, of course, the attacker website will try to create even more iframes and more processes, but the browser will now stop rendering the page and instead display a message informing the victim that the website is slowing down their device and leaving them with 2 options, either to leave the page or to stay. Leaving the page will simply close the tab and prevent any further damage. And selecting stay will also not enable the attacker to successfully conduct the attack, but it will merely increase the tab local limit of processes by a fixed value delta L, so that the attacker can just embed additional frames. So if we choose delta L to be 4, like the initial limit of L, the attacker could embed 4 more frames referencing different sites before the user would be prompted again to confirm the resource usage. Another advantage of that is, even though the attacker has exhausted the limit, this does not prevent the browser from operating. So the attacker website stopped rendering, but all other tabs will stay operational, and the victim can even open a new tab to benign.com that will be initialized with a new tab local limit L2, which is also initialized to 4. And of course, because the benign.com needs to be isolated as well, the limit will be reduced to 3, but benign.com can still operate and even reference additional sites. We did test our proof of concept mitigation with values L and delta L of 30, and we found that those prevent the fork bomb, prevent denial of service on the browser, and are unlikely to affect user experience. So we tested this against the Trunco top 1000 and saw that none of the websites triggered our dialog. Also, this countermeasure can utilize existing notification mechanisms that are already present in the browser for the exploits that run inside the browser sandbox. So this concludes my talk. Our artifacts are available via Zenodo. They're also available via GitLab Mirror at our institute. If you're interested, there's also Demon's demo video available via the Chromium bug tracker. I can also, after the talk, try to post the video via Slack. Or maybe we have time after the Q&A section to show a short demo. If you have any questions, please feel free to contact me here at the conference, via Slack, in person, or via email. So thank you for your attention, and I'll be happy to take any questions.